Welcome to the deep dive. Here, we take a stack of information, sift through the noise, and pull out the core insights that matter most for you.
Exactly. No need to dig through dense material. We'll guide you right to the good stuff.
We really focus on understanding why things are important, drawing from the sources you share.
And today, we're jumping into a really fundamental problem in computer science and data analysis. It's something you'll definitely bump into if you work with data. It's called the top K problem.
Yeah, it sounds maybe a little abstract, top K, but the core idea is incredibly practical. It probably affects your daily life in ways you don't even realize.
It absolutely does. I mean, think about it. You have a list of things, maybe millions of items, sensor readings, whatever, numbers in an array.
Right.
The top K problem is just about how you find the GAC items with the highest values. And crucially, how you do it efficiently.
Like finding the top 5 search results, maybe. Or the 10 biggest files on your hard drive. Exactly. Or, as our source from Hello Algo puts it more formally, given an unordered list of numbers, nums, of length n, return the largest k elements.
Simple definition. But the efficiency part is key. Finding the single largest number, that's easy, right?
Yeah, piece of cake. You just scan through the list once, keep track of the max, done.
But finding the K largest, say the top 100 out of a million, that's where things get interesting. The naive ways might be too slow.
And we've got this great source that walks through a few different ways to tackle this, looking at the trade-offs.
Understanding these different approaches is so important. It's not just how to find the top K, but knowing why you choose one method over another depending on the situation. That's crucial for building systems that actually perform well with big data.
Okay, let's unpack this then. Where does the source start?
Well, it starts with probably the most intuitive way you might think of doing it. They call it iterative selection.
Method 1, iterative selection. Okay, yeah, that sounds like how you'd maybe do it by hand with a short list.
Totally. You scan through the whole list, find the single biggest element, write it down.
Got it.
Then you mentally or programmatically, ignore that one, you scan the remaining list to find the biggest element left. That's your second largest overall.
And you just keep doing that I times.
Exactly. You repeat the process K times. The source calls it performing K rounds of iterations, extracting the first, then the second, all the way to the K largest element.
Okay, conceptually simple, makes sense, but what's the catch, performance-wise?
Yes, the cost. That's where we talk about time complexity. It's how we measure how the algorithm's runtime scales with the input size.
Right.
For iterative selection, the time complexity is O.
Oh, okay, so the time grows based on both the number of items and the number of top items we want, K.
That's the one. And this immediately tells you something important about its limits, which the source highlights. This method is really only practical when K is much, much smaller than N, like tiny compared to N.
So if K is just 1 or 2, it's basically ON, which is fast.
Right, ON1 or ON2 is still linear time, essentially.
But wait, what if K isn't tiny? Say K is half of N, then it's like ONN2, which is basically ON2, isn't it?
It is, and ON2 is, well, notoriously slow for large inputs. It just doesn't scale well at all. Doubling an N could make it take 4 times longer.
Yikes. Okay, so iterative selection is simple to grasp, maybe good for teaching, or if you know N is small or K is like 1, 2, 3, but not a general solution.
Precisely. Its simplicity is its main draw, but the performance tanks quickly as K grows.
The source also had that interesting point, when K actually equals N.
Yeah. If you keep going for all N elements, finding the first biggest, second biggest, down to the nth biggest, you've effectively just performed selection sort.
You've sorted the whole list, even though you just asked for the top K.
Exactly. Which kind of highlights how inefficient it becomes. If K is large, you're basically doing the work of sorting anyway.
Well, that leads perfectly into method 2 then, just sorting the whole thing from the start.
Right. The next logical step. Take your list nums, use a standard sorting algorithm to sort the entire list, smallest to largest.
And then just pick the last K elements off the end.
Yep. Those are guaranteed to be the largest K. Simple as that.
This feels very straightforward to code, especially if your language has a built-in sort function. And sorting algorithms are pretty well optimized these days, aren't they?
They are. If you use an efficient one, like merge sort or quick sort, the time complexity to sort n elements is typically O(n) log n.
O(n) log n. Okay, how does that compare to the OONT from the first method?
O(n) log n is generally much, much better than ON2. And it's usually better than ON whenever T gets larger than log n. Since log n grows way slower than n, this means sorting usually beats iterative selection for any significant value of K.
So for most cases where k isn't incredibly tiny, sorting is faster than that iterative approach. Seems like a pretty good option then, just sort and pick.
It is a solid option and often simple to implement, but the source makes a really insightful point about it. It says sorting kind of overachieves.
Overachieves. How so?
Well, think about it. You only needed to know which elements were in the top k. But by sorting the entire array of n elements, you've actually figured out the exact rank of every single element relative to all the others.
Ah, I see. You've precisely ordered elements, say, rank 500,000th and 500,000 first, even though you only cared about the top 100.
Exactly. You did all this extra work comparing and positioning elements way down the list that were clearly never going to be in the top k. It wasn't strictly necessary for the goal.
That makes sense. You did more work than was minimally required just to identify that top group, which suggests maybe there's a way to avoid all that extra sorting effort for the elements we don't care about.
Precisely. And that brings us nicely to the third method, the source details.
Yeah.
This one is often the most efficient, kind of the gold standard for the general top k problem. It's the heap-based approach.
Okay, heaps. This involves a specific data structure, right? And the source mentions using a min-heap to find the largest ek elements. That feels a bit backward. Wouldn't you use a max-heap?
It does seem counterintuitive at first, but it's actually quite clever. Let's walk through the steps exactly as the source describes, and you'll see why the min-heap works perfectly here for finding the largest k.
All right, I'm listening.
Okay, step 1. You initialize an empty min-heap. Remember, the key property of a min-heap is that the smallest element inside it is always right at the top, the root. Easy to peek at, easy to remove.
Got it. Min-heap. Smallest element at the top.
Step 2. You take the first k elements from your input array, nums, and you just insert them all into this min-heap.
Okay, so now the heap contains k items, and the smallest of those first k is sitting right at the top.
Exactly. Now, step 3. You start iterating through the rest of the array. So from the k plus 1 element all the way to the end, element n.
Right, processing the remaining nk elements one by one.
Step 4. For each of these elements you're looking at now, you compare it to the element currently at the top of your min-heap. Remember, that top element is the smallest among the potential top k candidates you're currently holding on to.
Okay, comparing the current array element to the smallest one in the heap.
And step 5. This is the crucial check. If the current element from the array is greater than the element at the top of the heap.
Uh-huh. If the new guy is bigger than the smallest guy currently in my top k group.
Then this new element deserves to be in the top k.
Right.
It's larger than the current weakest link in your candidate pool. So what do? You remove the smallest element from the heap, pop the root
Get rid of the smallest one.
and then you insert the current larger element into the heap.
Okay, swap out the minimum for this new, bigger element, and the heap property takes care of rearranging things.
Exactly. When you remove the root and insert a new element, the heap automatically reorganizes itself efficiently to maintain the min-heap property. The new smallest of the icky elements will bubble up to the top. And importantly, this operation, removing the min and inserting, takes about a log time.
Log k time. Okay, so that was step 5. What's step 6? What if the current element is not bigger than the top of the heap?
Good question. Step 6. If the current element you're looking at is smaller than or equal to the element at the top of the heap.
Then it means this new element is definitely smaller than at least one element already in my group of k, so it can't possibly be one of the overall top k elements from the whole list.
Precisely. So you just ignore it, discard it, move on to the next element in the array. It's not relevant to the final top k.
Makes sense. Saves work. And step 7, after you've gone through all n elements in the original array this way.
The k elements that are left sitting inside your min-heap are the largest k elements from the entire original array. You've effectively kept a running group of the k largest seen so far, efficiently updating it whenever a new, larger element came along.
That process feels really efficient. The heap never gets bigger than size k, right? You're not trying to organize the whole element list.
Exactly right. And that efficiency shows up in its time complexity. The source states it as O(n log k).
O(n log k). Okay, let's break that down again like before. Kn comes from iterating through all the elements.
Yep, you touch every element once.
And the log k part, that's from the heap operations, like the removal and insertion.
That's it. For each of the n elements, well, roughly after the initial k, you do a comparison and maybe a heap removal and insertion. Those heap operations take O log k time because the heap size is capped at k. So you do about n operations, and the potentially costly part of each operation is logarithmic in k. Gives you O(n log k overall.
Okay, I think I get the O(n log k. Now let's compare. We had O(n) log n, O(n) log n for sorting, and now O(n) log k for the heap. How does O(n) log k really stack up in practice?
This is why the heap method is generally preferred. It strikes a fantastic balance. Look, when k is very small, log k is also very small, almost a constant. So O(n) log k behaves almost like O(n), nearly as fast as the best case for iterative selection.
Okay, good for small k. What about larger k?
As k gets larger, log k grows, but it grows much, much slower than k itself. So O(n) log k is significantly faster than O(n) for almost any practical value of k.
Right, and compared to sorting's O(n) log n.
Well, since k is always less than or equal to n, log k is always less than or equal to log n. If k is noticeably smaller than n, which is common in top k problems, then log k will be noticeably smaller than log n.
Meaning O(n) log k will be faster than O(n) log n.
Exactly. Remember how sorting overachieved? It paid the O log n cost per element to get everything ordered. The heap method is smarter. It only pays the O log k cost per element, just enough work to figure out if an element belongs in the current top k candidate pool. It avoids sorting the irrelevant smaller elements.
That really clarifies it. Sorting compares everything to figure out the full order. The heap cleverly only compares a new element against the current boundary of the top k, the smallest one in the heap. If it's not bigger, it ignores it. If it is bigger, it efficiently swaks it in with just log k work. Much less effort overall if kn.
You've got it. That O(n) log k performance makes the heap approach super efficient and versatile for finding top or t elements in lots of different scenarios. And the source also points out another cool advantage: its suitability for dynamic data streams.
Oh, right, you mentioned that. Where data isn't all available at once but arrives continuously.
Yeah, exactly. Imagine you have data pouring in constantly. You can just maintain your min-heap of size k. As each new data point arrives, you do that quick comparison with the heap's top element.
If it's bigger, you pop the min and insert the new one, O log k work.
If it's smaller, you just discard it O1 work. This lets you keep track of the top k elements seen so far in real time, without needing to store the whole, potentially infinite stream of data.
That's a really powerful application. Shows this isn't just about static lists you have up front. It works for evolving data, too.
It absolutely does. Very practical.
Okay, wow. So we've really taken a deep dive into this top K problem. We looked at 3 distinct paths. The simple, kind of brute force, iterative selection.
Straightforward, sort everything, then pick method.
And then this quite clever and generally much more efficient heap-based approach using a min-heap.
And we've nailed down their time complexities: O(n) log n and O(n) log k. Understanding these is key because it shows why O(n) log k often hits that sweet spot for performance.
It really highlights the trade-offs, doesn't it? Simplicity versus raw speed. Iterative is easy to think about, but often slow. Sorting is also easy to code, but can be overkill.
While the heap method needs a bit more understanding of the data structure, but it pays off with the best general-purpose efficiency, tailoring the work much better to the actual problem of finding just the top k.
And knowing this stuff isn't just theoretical CS trivia. It's fundamental if you're building systems that need to handle large amounts of data efficiently. Choosing the right approach matters.
It really does. Having these techniques in your toolkit and knowing when to use which is a huge advantage for tackling real-world data challenges effectively.
Absolutely. Okay, here's something to maybe chew on until our next deep dive, building on the source's focus on time. We spent a lot of effort talking about how fast these methods are.
Right, the time complexity.
But what about the space they use? You know, the memory requirements. Does sorting, for instance, need more temporary memory than the heap method? Or less?
That's a great question. Time efficiency is often the first thing we look at. But space complexity, how much memory an algorithm needs, is also a critical resource constraint, especially with massive data sets.
Yeah, sometimes optimizing for time might cost you more memory, or vice versa. It's another trade-off to consider.
Definitely something to keep in mind.
So keep that question simmering as you encounter data problems out there. Thanks for joining us for this deep dive.